In this work by Gabriele Costante and Thomas Ciarfuglia, a latent space representation for optical flow images is learned together with the visual odometry task. The aim of this technique is to improve generalization and robustness to covariate shifts for data-driven visual odometry systems. In the past 2 years, a number of data-driven visual odometry systems have shown that the camera ego motion estimation can be solved effectively by deep neural networks, which may be fused with geometrical methods or with inertial sensors. However, the main weakness of data-driven approaches is the learning bias that is generated during training. This bias becomes evident when we try to use the model on different input data, such as when we pass from Kitty dataset to other driving datasets. Since the optical flow field that is used for prediction depends both on scene appearance and camera motion, one of the arising questions is how do we disentangle the contribution of the motion from the bias-generating contribution of scene appearance? We propose a first step in this direction by trying to learn a latent space representation of the optical flow field. This representation lives on a lower dimensional manifold that we try to learn with an autoencoder. The main idea of this work is that by learning together the optical flow subspace and concurrently using it to learn an ego motion estimation task, we're able to find a more robust representation of the input space that has better performances when faced with covariate shifts. The input are pairs of images, and the first part of the network is FlowNet. The two branches are the decode part of the autoencoder for learning the optical flow subspace, and a standard convolutional VO architecture to learn the motion estimate. Both error signals back-propagate to the encoder part of the autoencoder. The features learnt in this way are well suited for motion estimation. We performed a large number of experiments using Kitty and Malaga 2013 datasets, training on normal sequences and testing on unseen sequences modified with heavy blur and different speed to simulate covariate shift. We compared both with state-of-the-art geometrical methods and data-driven methods. Our experiments show that learning the latent optical flow space is able to increase performances in general and make the architecture more robust to covariate shifts.